Hi, welcome to my channel. I'm your host GL, and today I'd like to talk about magnetic separation. Magnetic separation is a technique that uses magnetic forces to separate magnetic materials from non-magnetic ones. It's like having a superpowered magnet that can pick out specific materials from a mixture. You know, I always tell my students to think of it like a really picky eater at a buffet. Just as a picky eater only chooses certain foods and leaves others behind, the magnet only attracts magnetic materials and ignores everything else. The science behind it is pretty neat, actually. When we bring a magnet close to a mixture, it creates a magnetic field that induces magnetism in materials that can be magnetized. These materials then stick to the magnet, while the non-magnetic materials just sit there thinking, not interested. The main materials we can separate using magnets are ferromagnetic substances like iron, nickel, cobalt, and their compounds, plus some rare earth elements. These materials are strongly attracted to magnets. Let me break this down with a kitchen analogy that I use in my class. Imagine you've got a bowl of cereal with some iron-fortified breakfast flakes. If you held a strong magnet over it, those iron-enriched pieces would actually be attracted to the magnet. Pretty wild, right? In industry, we're dealing with much bigger stuff, of course. But the principle is exactly the same. Some materials come running to the magnet like teenagers to a pizza party, while others just couldn't care less. One of the most common industrial applications is in mining and ore processing, where magnetic separation is used to extract valuable iron ore from raw mine materials. This process helps mining companies get the good stuff while leaving the worthless rock behind. Think about it like this: when you're hunting for your keys in a messy drawer, wouldn't it be amazing if you could just wave a magic wand and have your keys jump right out? Well, that's basically what mining companies do, except their keys are valuable iron ore, and their magic wand is an industrial-strength magnetic separator. These machines can process tons of material per hour, and they're working 24/7 in mining operations worldwide. It's like having a tireless robot with a really strong arm, picking out all the valuable bits from the rocky soup. The stronger the magnet, the more effectively it can attract magnetic materials, and the better it can separate even weakly magnetic substances. Magnet strength directly impacts both the speed and accuracy of the separation process. It's kind of like fishing with different sized nets. A weak magnet is like using a net with big holes. You'll only catch the big fish, or in our case, the strongly magnetic materials. But a strong magnet? That's like having a superfine net that can catch even the tiny fish. I once demonstrated this in class using two different magnets to separate iron filings from sand. The stronger magnet picked up more iron filings and could do it from a greater distance, while the weaker one was like that one student who sits in the back of the class, not quite reaching its full potential. Magnetic separation is cost-effective, environmentally friendly, and requires no chemicals. It's also a continuous process that can handle large volumes of materials while being relatively low maintenance. I like to tell my students it's like having a super efficient cleaning robot versus hiring a cleaning crew. The robot, our magnetic separator, never gets tired, doesn't need lunch breaks, and won't call in sick. Plus, it's environmentally friendly, unlike some chemical separation methods that are about as gentle on the environment as a bull in a china shop. And here's the kicker: it's like having a bouncer at a club who only lets in specific people, but this bouncer works for practically pennies per hour. Talk about a bargain. And by the way, if you are enjoying the video so far, do me a quick favor. Hit that like button. It really helps support the channel. And it only takes a second. Particle size significantly affects magnetic separation efficiency. Generally, particles that are too large or too small can reduce separation effectiveness, so there's usually an optimal size range for each specific application. Let me put it this way: imagine you're trying to sort M&Ms by color, but some are regular-sized, others are mini, and some are giant party-sized ones. It would be pretty tricky, right? That's exactly what we're dealing with in magnetic separation. If particles are too big, they might be too heavy for the magnetic force to lift them effectively, like trying to pick up a bowling ball with a refrigerator magnet. Too small, and they might clump together like teenagers at a school dance, making it hard to separate them properly. The sweet spot is like Goldilocks porridge: not too big, not too small, but just right. Ferromagnetic materials are strongly attracted to magnets, paramagnetic materials are weakly attracted, and diamagnetic materials are slightly repelled by magnetic fields. These different behaviors determine how easily materials can be separated using magnets. I love explaining this one to my students using a high school dating analogy. Think of ferromagnetic materials as that person who's immediately and strongly attracted to someone. They're the first ones to respond to any attention, just like iron to a magnet. Paramagnetic materials are like the shy ones who show some interest but need a lot more encouragement. They're attracted, but weakly. And diamagnetic materials? They're like the complete opposite. They actually back away slightly when approached, just like how some students react when I announce a pop quiz. Magnetic separation is crucial in recycling facilities for separating ferrous metals like steel and iron from other waste materials. It's a key step in processing everything from household recycling to industrial waste. Think of a recycling facility as a massive kitchen where we're trying to sort out all the ingredients that got mixed up. The magnetic separators are like our master chefs, but instead of picking out ingredients by hand, they're using magnetic fields to grab all the metal items. You've probably seen those giant electromagnets at scrapyards, swinging around and picking up cars like they're toys. That's magnetic separation on steroids. In fact, next time you're enjoying a can of soda, remember that the aluminum can you're holding might have been sorted using magnetic separation. Though aluminum itself isn't magnetic, the process helps separate it from other materials by removing the magnetic ones first. Pretty cool, right? If you're looking for exercises to test your knowledge, there is a link in the description for you. Thanks for sticking around till the end. If you enjoyed the video so far and want to see more content like this, make sure you hit that subscribe button. Thanks for watching.